I've now analyzed bovine serum albumin, or BSA, a common small protein, with the Delcimax Pro. The BSA was 2 mg per mil in concentration, and it's in phosphate buffer saline, which is a pretty common solvent for proteins. Based on its size, which is about 66, 67 kilodaltons, and the concentration, we probably could have measured the size and zeta potential in BSA in as little as 2 seconds. However, I took 2 measurements instead, one which lasted 25 seconds, and the other which lasted 120 seconds. For both experiments, a 3.5 volt voltage amplitude was applied, while the voltage can be adjusted from 1 up to 100 volts, depending on your solvent and its conductivity. But proteins in buffer tend to be easily destroyed by electricity, so voltages between about 2.5 to 3.5 volts are optimal, and it's what we recommend. Measurement 1 lasted 25 seconds and gives a zeta potential of minus 15.4 millivolts. So we can go click on the mobility graph, clicking on the PALS tab, then on the mobility graph, and we can see how all 31 independent measurements match up of the zeta potential. As we see here, 30 out of the 31 measurements tend to agree and show the same shape of the V curve. One measurement is slightly off, this higher V curve right here. This is probably caused by a speck of dust in the measurement flow cell scattering light into one of the detectors. Remember, working with clean, dust-free samples is very important with dynamic light scattering and zeta potential. But by having 31 independent detectors, we can be sure that our zeta potential measurement is accurate, and even if a speck of dust influences one of the detectors, we can still analyze the other 30 detectors to get an accurate value. Now we'll go ahead and look at the size of the BSA by clicking on the regularization graph tab. We see here that the BSA has a diameter of 6.5 nanometers, which is as expected, without any large aggregates present. We can look at the histogram on the graph to get a visual idea of what the distribution of the size of the BSA is. And for the most part, the size ranges from just about 5 nanometers up to 8 nanometers in size with limited polydispersity. So we can accurately characterize the stability and the size of this small common protein BSA in as little as 25 seconds with the Delcimax Pro. Now, interestingly, if we run the BSA for longer times, we begin to see that the protein aggregates and essentially burns under the longer time period of electrical voltage. With measurement 2, we see that it's identical to measurement 1 in every way except for it's run for a longer time, 120 seconds instead of 25 seconds. In this time, we can see that the size distribution now begins to include large aggregates that are hundreds of nanometers in diameter, with an average size of around 760 nanometers. Also, we can look at the mobility graph, and we see that now we have an inverted V-shaped graph for all 31 detectors. This indicates that the mobility and zeta potential have now shifted positive, and this shift in zeta potential is a strong indicator that there's been damage to the protein by the electricity. This experiment highlights the importance of speed and zeta potential measurements of proteins. Because many proteins are very fragile in nature and are just held together by very tenuous bonds, the Delcimax is designed with massively parallel mobility detectors to reduce the measurement time down to a few seconds, which gives the researcher the most accurate data available.